Chapter 6, Section 1, Ionic Bonding. There are a few things that we need to go over from Chapter 5 before we really get into what ionic bonding is. The first is a stable electron configuration, and that's when you have your highest occupied energy level, or the outermost shell, that is completely full of electrons. That means the atom is completely stable and was unlikely to react. So think about all of your group 18 elements. So helium, neon, argon, krypton, all of those have a completely full and satisfied energy shell. Now with this electron configuration, we talked briefly about dot diagrams. And that's a model of an atom where a dot represents a valence electron, and I put all those up on the board for you to see. For example, here is krypton. You can see it has 8 dots to represent that it has 8 valence electrons. All right, that means it's completely full and happy. And we're going to add dot diagrams to our booklets. The other thing that you need to know, though, is oxidation number. And this is where we kind of start getting into how things bond together. So why they're placed in certain places that they are. So, for example, this is the ones that we're really going to look at. So hydrogen through argon. So starting with hydrogen, lithium, and sodium, all of those are in the same column. They're in the same group, the same family. So all of those, if you look at them, have 1 electron in their outside shell. That means they have 1 too many. So 1 plus. That means they can get rid of one of them by combining with someone else. Moving on to group 2, you can see that they have 2 valence electrons, or 2 in the outside shell. That means they likely want to get rid of 2 of their electrons. Same thing, moving on to group 13, boron and aluminum, 3 plus. They have 3 electrons too many, 3 that they can get rid of. Now when we hit the next group, group 14, which has carbon and silicon, this group gets a little different. This is a plus or a minus group. That means it can either have 4 too many that it wants to get rid of, or maybe that it has 4 too few that it wants to take in. Then we move on to group 15, nitrogen and phosphorus. That means they have 5 electrons in their outside shell. Instead of getting rid of those 5, it's easier for them to collect 3 more. So they need 3 electrons. That's why it's 3 minus. They need 3 more negatives to be satisfied and happy. Moving on down the list, we have oxygen and sulfur. They need 2 more electrons to be satisfied and happy. In group 17, fluorine and chlorine need 1 electron to make them full and happy. Now, as far as full and happy goes, helium, neon, and argon are already there. They already have a completely full outside shell. So their oxidation number for bonding is 0, because they don't need any other electrons at all, or need to get rid of any, to be happy. And we're going to use these numbers in just a few minutes. So looking at ionic bonds, that means that some of these electrons and combinations we get happen by a transfer of electrons. So the giving and the taking of electrons. So for example, sodium, which is in group 1 and has 1 too many, and chlorine, which is in group 17 and has 1 too few, they want to transfer. They want to trade out an electron. So if sodium gets rid of an electron, it becomes more positive and now has a second energy level, as you can see right here, that is completely full. Chlorine gains that electron and now has a third energy level that is completely full and happy. So it becomes more negative because now it has 1 more electron than it does protons. So this is where I got to telling you guys that for this class, protons and electrons for 1 atom of that element is neutral. That way it makes it nice when we go to bond things. All right? So that's our ionic bonding. Now, when we bond ions, we have the term ion. That means it's just an atom that either has a positive or negative electric charge. A positive or negative electric charge. An anion is the negative charge. Okay, so an is negative. It's kind of like dissing or one of those. A cation, cats are positive, so that's your positive charges. So anything with a plus oxidation is a cation. Anything with a negative oxidation number is an anion. Now, as far as bonding goes, your chemical bond is your force that holds those things together as one big unit. And with ions, that force is specific to cations and anions. And we have what's called a chemical formula. And this is just a way to represent what elements you have, the ratio of those elements, and how many of those elements you have in the compound. So for example, MgCl2. That shows you that you have one magnesium because Mg is there, kind of like in math, if you have an X, it represents one X. And then you have Cl2, that means you have two chlorines. So one magnesium has two valence electrons. Chlorine needs one electron, so to satisfy magnesium getting rid of two, it needs to give it to two chlorines, one to each. So magnesium is a 2 plus, we already looked at that, and chlorine is actually a 1 minus. All right, so that's from your oxidation numbers that we already looked at. Now, the other type of bonding is covalent bonding, and this is a little bit different from ionic. Covalent is where we now share the valence electrons. So it's no longer here, you can have this, I'm done with it. Or, hey, I need that, I'm going to take it, it's mine forever. It's now that we're going to share that piece. So when you think of covalent bonds, think of something that can't get rid of it. For example, hydrogen has one electron. It would like to get rid of it, but then it would have no electrons whatsoever, and that's not possible. So hydrogen has to always combine covalently. It has to always share. We'll take a look a little bit. You can see here water is actually polar. That means that hydrogen has a smaller charge than oxygen. And I'll show you a pretty neat trick with polar covalent bonds because it actually gives it a special charge. We also have what's known as molecules. It's a neutral group of atoms that are joined together by covalent bonds. And then, of course, we have, like I said, the polar covalent bonds. So if it's polar, the bonds aren't shared equally. So the one that has the greater attraction will have negative, and the other one will have partial positive. So neither one of them is completely negative or positive. And water is the best example. So when I say polar versus nonpolar, think about it this way. If you were to bond one carbon atom with two oxygen atoms, it would look like this top image. All of those look relatively the same in size. However, if you were to bond two hydrogens with one oxygen, you can see the size of these atoms are completely skewed. So hydrogen is actually a lot smaller in size than oxygen. And that's it for today.